So here we have a rational function. So if we start with our intercepts, again, the y-intercept is easy because you can just plug in 0 for x. And this one's easy to see that it's going to be 1/4. Our x-intercept is very nice for writing int there. Our x-intercept is when we make y equal to 0. So now if we make y equal to 0, and we have 3x plus 1 over 2x plus 4, whenever you have a fraction equal to 0, the only way that fraction is equal to 0 is if the numerator is equal to 0. Now, the mathematical reason for that is if you wanted to get rid of the fraction, you could multiply both sides by 2x plus 4. If you multiplied by both sides by 2x plus 4, this side would still be 0, and the 2x plus 4 would disappear on the other side. Either way, when you solve for x, it's whenever the numerator was equal to 0. So we have our x-intercepts and our y-intercepts. Now, the second thing we look for, and this is why this question is a good one, is asymptotes. Because this graph does have asymptotes. The easiest one to look for are the vertical ones. The vertical asymptotes happen when you have a non-permissible value. And a non-permissible value happens when you divide by 0. Since this is a rational function, we have a possibility of dividing by 0. Can you see what value would make you divide by 0? -2. That will be your vertical asymptote. So because -2 is a non-permissible value, you're going to have an asymptote at x equals -2. To figure out if your function has a horizontal asymptote, and this one does, you're basically looking at a limit. What's the limit of this function as x gets really, really big? Right? As x gets really, really big, that limit's going to equal 3/2. And so our horizontal asymptote will be that when x gets really, really big, we're going to have a horizontal asymptote at y equals 3/2. So first of all, intercepts and asymptotes we can find using mathematics that we've done before. Now to find out where it's increasing, decreasing, or stationary points, inflection points, we're going to need to do our derivative and our second derivative. So in this case, for our first derivative, we have a quotient. So we're going to use our quotient rule. Keep the bottom the same. Derivative of the top minus keep the top the same. Derivative of the bottom over the bottom squared. Now because I'm going to do a second derivative after this, it's going to make sense to simplify this a little bit. On the top, if we multiply things out, it works out really nicely. The 6x's go away, and we're just left with 10 over 2x plus 4 squared. Now to find out if we have any stationary points, we need to make our first derivative equal to 0. Sorry? How come it's squared on the bottom? Well, right now, the temptation is to cancel it here, but because of this minus sign there, this is all grouped together. So unless you can factor out a 2x plus 4 out of both of those, you won't be able to simplify it. Again, when you make it equal to 0, a fraction is only equal to 0 if the numerator is equal to 0. Can you see that this one never equals 0? So as far as our number line goes, we have no stationary points. That being said, when we did our number line, we included our stationary points and other critical points, which included non-permissible values. We have a non-permissible value at x equals -2. So that would be something that you would still put on your sign diagram here. And checking your value before -2 and after -2, plugging that into your derivative, can you see in your derivative, once you've simplified it to 10 over 2x plus 4 squared, that 10 is always positive, and 2x plus 4, when it gets squared, is always going to be positive. So no matter what number you plug in here, this function is always going to be increasing. Yes? How did I get the -2? That came all the way up from here, the fact that we have a non-permissible value that x can't equal -2. From our original equation, that would make us divide by 0. So it's never equal to 0, and we find out that our function is always increasing. We still had to include -2 on our number line, because at an asymptote, it could change from increasing to decreasing. But in this case, it doesn't. Now, right beside this, now that I've simplified my derivative to 10 over 2x plus 4 squared, I am going to do my second derivative right beside. So I'm going to just rewrite my first derivative was 10 over 2x plus 4 squared. I'm going to want to find my second derivative. I could use my quotient rule again. I could also take, and I think this will be easier in this case, I'm going to take the 2x plus 4 and write it as a -2 and use a chain rule to find the second derivative instead. So using the chain rule, 2 comes out in front, subtract 1 from the exponent, multiply by the derivative of the inside. Simplifying this, we're going to get -40 over 2x plus 4 cubed. Again, just like before, the only way that would equal 0 is if our numerator is equal to 0, so it's never equal to 0. So when I do my sign diagram to figure out concavity, again, I still have to include my non-permissible value, because that's a critical point on there, and I'm going to check values before -2 and after -2. So if you plug a number in before -2, can you see that you're going to get 2x plus 4 is going to be negative, and when it gets cubed, it's still going to be negative on the bottom, and a negative number divided by a negative number will be positive. However, any number after -2, the bottom will be positive. The top is still -40. This will be negative. This will be concave down. So this question is a little bit easier in that you don't have to find any stationary points or find any inflection points. There's no stationary points. There's no inflection points. But sometimes having less information can make it a little bit harder when you go to graph it, just because you have less things to do. So now what we're going to do is we're going to put everything that we know on here and then see if we have enough information to graph this. Set up my grid. What I do know is that at -2, I have one asymptote. At y equals 1.5, or 3/2, I have another asymptote. I figured out my x-intercept and y-intercept right from the beginning. So if we scroll up just to see what those values were, our x-intercept was -1/3 and our y-intercept was 1/4. So our y-intercept is at 1/4, so we can label that 0, 1/4. And -1/3, 0 is our x-intercept. As far as graphing this from our sign diagrams, we know that the section before -2 has to be increasing, and it has to be concave up. So considering that on this side, you have two possibilities. You can have the graph above the asymptote or below the horizontal asymptote. Can you see that the only way that you could be increasing is if you started above the horizontal asymptote? And the only way it could be concave up is that situation as well. Now to the right of x equals -2 is a little bit easier because you have a couple of points you know your graph has to go through. Again, it has to be increasing and it has to be concave down. So that part was a little bit easier. We are technically done this graph as a personal preference whenever I'm graphing something that has asymptotes like this. I've got a couple of points labeled in this section to the right. I have nothing labeled to this section to the left. Sometimes I like to just add a point by plugging it into my original equation just so I have some sort of reference point. So if I plugged in -3, what would I get? So my original function was 3x plus 1 over 2x plus 4. If I plug in -3 for x, can you see that at the top I'm going to get -8? And on the bottom, -6 plus 4 is -2. That's going to simplify to +4. So I might label one point in that section just to give it some sort of stability or a reference point. But I can do that by just plugging in a value. It's not a critical point. It's not an inflection point. It just makes one point in that section. And it kind of verifies that, yes, we drew it in the right section, that it has to be above that horizontal asymptote. So the rational graph is a little bit different. It didn't end up having any maximum points or any minimum points or any inflection points. So it was really critical that we had our asymptotes from the beginning and our x-intercepts added to it, but our first derivative and our second derivative still told us things about the concavity, about where it was increasing and decreasing, so we knew where to graph the different sections.